All right, assignment 18. This is 5.3. Solving quadratic equations by square roots. All right, and our essential question. What are properties of square roots how do you solve quadratic equations by square roots? All right, so far you've solved quadratic equations by factoring, and this is just another method that sometimes can be used. So let's review square roots and their properties, okay? So a square root basically, if I have that r equals the square root of s, that is true if and only if r squared equals s. Right? Because I could then, for example, here I could square both sides and get this. Okay? And then the reverse is also true. So I could, if I wanted to get r by itself, I could square root both sides. The trick is, so let me give you a trick. So what if I said that x squared equals 25? And then what is x? Well, if I square rooted both sides to get x by itself, you would say, well, x is 5. But is that true? Is that the only number that I can square to get 25? There's another number that I can square to get 25. And hopefully you're saying to yourself, oh yeah, you could also square a -5 and get 25. So anytime you're solving this type of equation, you want to remember you're going to have two possibilities, right? Two things that you could potentially square to get what you originally started with. So let's talk about properties of square roots. All right, so one of them is the product property of square roots, and this becomes pretty handy. All right, so the first one has to do with multiplying or with looking for factors under the radical. So we'll call this, if we have the product. Okay, so if I have, for example, the square root of a times b, well, that could be the same thing as the square root of a times the square root of b. Okay, so let me just give you an example. I'll do an IE under that. So if I, for example, had the square root of 75. Well, the square root of 75 is really the same thing as the square root of 25 times 3. So I can really break that up. I can say, well, this is really the square root of 25 times the square root of 3. And this gives you a better way of handling it. Okay, and I know that we reviewed this in geometry. And so the square root of 25 is 5. Right, so the square root of 75 is really 5 root 3. Okay, so that's when you have a product. Okay, you can basically take that product that's under the radical and break it up into the product of two radicals. Now, what if we have a quotient? So, for example, you have the square root of a over b. Same thing applies. So you can actually take this and you can break it up so that you have the square root of a over the square root of b. So as an example of that, what if I had, I don't know, how about 28 over 49? So I might want to break this up so that I can deal with these individually. So this would really be the square root of 28 over the square root of 49. And now I might want to go back and use my product property here. So 28 is really the square root of 7 times the square root of 4. And the square root of 49 is really 7. Okay, well I can't take the square root of 7, but I can take the square root of 4. So that gives me 2 root 7 over 7. Now realize root 7 is really some number between, let's see, 2 and 3, right? Because 2 squared is 4 and 3 squared is 9. Okay? So these two are not, they're not a common factor at all. This is somewhere between 2 and 3. This is actually 7. Okay? So this would be my final, most simplified answer. Let's talk about simplifying. So when is a radical simplified? Again, this is something that we reviewed last year. So a radical is simplified when two things must be true. No perfect square in the radicand. That's the number under the radical. And no radical in the denominator. Okay, so these are important. So make sure that you've got these. If you don't already know them, you need to know them. Okay? So one way, sometimes we end up with a radical in the denominator, and we want to get rid of that radical in the denominator. And so we do a thing called, so in order to get rid of the radical in the denominator, you could use rationalize, or I should say you can rationalize the denominator. So this is important. And what this does is it gets rid of radical in the denominator. Okay, so let me give you an example of that. So I'll do an IE. Let's say I have now the square root of 7 over 2. Okay, well let me remind you, we can then break that up to the square root of 7 over the square root of 2. Now can either one of these, can I actually take the square root of either of them? I cannot. However, my problem is, I'm going to end up, if I leave this alone, I'm going to end up with a radical in my denominator, and that means it's not completely simplified. So in order to get rid of that radical, we do a thing called rationalizing the denominator to get rid of it. So the way I can get rid of this radical is by multiplying it by itself. Top and bottom, because multiplying top and bottom is like multiplying by 1, right? Okay, so this really becomes then 7 times root 7 times root 2, which is really root 14, and root 2 times root 2, which is really root 4, which is 2. Or anytime you have a square root times a square root and they have the exact same number underneath it, you know that that's the same thing as like the square root of 2 squared. So let me write that on the side. So this is really the same thing as the square root of 2 squared. Well, what is an exponent and a radical? Those are opposites, right? So they cancel each other out, and you're just left with the 2. Now again, square root of 14 is not 14. Okay, it's some number between 3 and 4. So we cannot reduce here. So you just be left with this. All right, so let's actually solve some equations using these properties. We'll do 3 of these. Solve the equation. So again, if these are quadratics, that means that they're parabolas, and we're really just looking for the x-intercepts. Okay, so the first one, A, we're going to solve x squared equals 121. So I need to get x by itself. I have options. I can always get this into standard form, right? Subtract the 121 over here. I'd have a difference of 2 squares. I can factor it. That's totally doable. Here's another way to do it. You can basically take the square root of both sides. Okay, so if I square root something squared, I'm just left with this. Maybe you know this. I hope you do. The square root of 121, you're asking yourself what number multiplies by itself to get 121, and that's 11. But remember, there are 2 numbers that I can plug in for x that I can square to get 121. So x is going to equal 11. Sorry, positive or negative 11. I just said that, and then I wrote down the wrong thing, right? Because I can square negative 11, and I can still get 121. All right, let's do another one. So what if I have v squared over 25 minus 1 equals 11? All right, so the first thing I need to do, before I can start square rooting everything, I need to get v squared by itself. Okay, so first thing, get v squared by itself. So what's happening to v squared? Well, it's being subtracted by 1 and divided by 25. I'm going to undo addition or subtraction first. So I'm going to undo this minus 1. So I'm going to add 1 to both sides. Now I need to get v squared by itself, so I'm going to undo this division. So 12 times 25, well, let's see. 25 times 10 would be 250, plus another 2 25s. I think that's 300. So that's one way of going about it. But another way, and a lot of you guys like to do that, and that would be great if this was a perfect square, but it's not a perfect square. So it might be easier for me to leave it in this form and work with it that way. Or I can break it up here, okay? So I'm going to go ahead and erase that, just because I want to show you guys how you can leave it in this form and work with it. All right, so I need to get v by itself, which means I'm going to take the square root of both sides. So now I get v equals positive or negative. All right, well, I basically have the square root of 12, the square root of 25. I'm going to break that up using that product property. I know that the square root of 25 is 5. Square root of 12 can be broken up into the square root of 4 and the square root of 3. And I know that the square root of 4 is really 2. So I'm probably doing more steps here than you would, right? So you might have said, oh, well, that is 2. Let me just make this 10. But I want to show where it comes from. So this is really 10 root 3. Positive or negative 10 root 3. So you get either a positive one or a negative one. Okay, we're going to do one more example together. This one will look familiar to you, and you're going to say, what? I could have been doing that the whole time. All right, so C looks like this. So this to me looks a lot like a certain form. That's right, vertex form. So if I wanted to graph this right now, I could easily subtract 135, and I could either call that 0 or y. Right? So I would know that my vertex is at 7, negative 135. Okay? What we've been doing right now, or up until this point, if we wanted to find the x-intercepts, is we were distributing all this, right? So we were doing double distributing with x minus 7 squared, and then distributing the 5, and then bringing the 135 over, combining like terms, and then factoring it all, and then solving. That's a lot of work. When we can now use square roots to actually solve this. So I want to get x by itself. The first thing I need to do is get rid of this 5. It's being multiplied to x minus 7 squared, so I'm going to divide both sides by 5. I end up with x minus 7 squared equals, and 5 will go into this 27 times. Now I have the square root by itself, right? So that's always your goal. Or sorry, the squared thing by itself. That's always your goal. Get the thing that's being squared all by itself. So in order to undo being squared, I have to square root both sides. So I end up with an x minus 7 equals a positive or negative square root of 27. All right, still x is not by itself, and I also need to deal with this mess over here. So I think I'm going to choose to get x by itself, and then I'm going to deal with this. So I need to add 7 to both sides. Now I'm going to put the 7 in front here because remember, it's a positive or negative root 27. So I'm going to have the 7 in front of that positive or negative. They're not like terms, right? So right now, this being a radical, you can't actually combine them. You could put this into your calculator and combine them. I'm not going to do that, though. I'm just going to simplify it the best I possibly can and get a more accurate answer. So square root of 27, I know, is basically the square root of 9 times the square root of 3. The square root of 9 is 3, and I can't take the square root of 3. So I basically have 7 plus or minus 3 root 3. So what am I talking about here? There's going to be two potential answers, and this is going to be important for when we start graphing these, right? Because these are your x-intercepts. So right now, you can leave it in this form, but in another section or two, you're going to have to graph this, and you're going to have to know, well, where exactly is this? So it's important to realize that, the square root of 3 is somewhere between 1 and 2, right? Because it's somewhere between the square root of 1 and the square root of 4. So this is 7 plus 3 plus. Okay, we're not really sure exactly what this is. So this is where you would get your calculator out. Again, not necessarily for this lesson, unless they want exact decimals. So the square root of 3 is, well, first of all, it's an irrational number, but it's approximately 1.73. Okay, so really I'm going to do 7 plus 3 root 3, and then 7 minus 3 root 3. Okay, so those are going to be my two solutions. So 7 plus 3 root 3. Oops, that's division. We don't want that. So I'm getting 12. So I'm going to actually write that down. I got two answers here. So x is approximately 12 how about 196? And x is approximately, so now we would need to do it the other way, which is subtraction. Also, we're going to be doing quadratic formulas, so there will be a whole bunch of these plus or minuses happening in your life in the very near future. So 7 minus 3 root 3. I get approximately 1.804, let's call it. Oops, not 8. 1.804. 0, 4. So really, this is what I'm looking for. But if you had to graph it, you might want to know where those x-intercepts are on your graph. So putting them into decimal form would be way more helpful. For this lesson, though, you can just simplify things. And I would prefer that you do that. Okay, so let's apply this. This is going to be example 2, page 267, number 18. So here it is. It's an engineering problem. So at an engineering school, students are challenged to design a container that prevents an egg from breaking when dropped from a height of 50 feet. Some of you may have done this in junior high. Write an equation giving the container's height, h, in feet above the ground after t seconds. How long does the container take to hit the ground? So, let me draw your attention back to your quadratic modeling handout. This is where we reviewed will it hit the hoop, and we did an Elton Brand problem. And one of the examples on here was projectile motion. And we said that any projectile motion can be modeled using this equation, where V naught is your initial velocity and h naught is your initial height. Okay, so we're going to apply that to this problem. So I'm just going to rewrite that equation. H of t is negative 16t squared plus v naught times t, or time, plus h naught. Okay, where v naught is your initial velocity and h naught is your initial height. So going back to this problem, I guess the two things that we need to look at are what is our v naught, or our initial velocity, and what is our h naught, or our initial height. And then we can just plug those in and we can have our equation, and then we can either graph it or we can solve it to figure out the information being asked. So first of all, the egg is being dropped. So if it's being dropped, that means that nobody's actually throwing it. So your initial velocity on this one becomes 0. Okay, and now we just need our initial height. So if I'm looking at this, it is being dropped from a height of 50 feet. So our h naught is going to be 50. All right, so let's do this again. So h of t then becomes, well, leave that negative 16t squared. That has to do with the acceleration of gravity. Plus, there was no initial velocity. So if I plug a 0 in for v naught, that's going to get rid of this entire term. And then h naught is 50. Okay, so let's go back to the question. Write an equation giving a container's height in feet above the ground after t seconds. Well, I think we just did that. So that's part 1. And then the second part of this is, how long does it take the container to hit the ground? So if the container is going to hit the ground, I know then that my output, or my height, is going to be 0. So I can plug 0 in there. So basically all I'm looking for is one of my roots. Now, because I don't have that t term, or that middle term, this becomes a problem where I can just solve this using square roots. So I think I'll want to get this term to be positive, so I'm going to add that term to both sides. I always like my x squared, or whatever variable I have being squared, I like to have it positive. Now I'm going to solve for t squared. And now I'm going to take the square root of both sides. So it's going to be the square root of 50 over 16, the positive or negative, which means I basically am going to have two answers, right? I'm going to have a positive answer and a negative answer. So let's simplify. Square root of 50, well, that's really the same thing as the square root of 25 times the square root of 2 over the square root of 16. So this is really t equals positive or negative, square root of 25 is 5, over the square root of 16, which is 4. Now to get a more accurate understanding of what is happening, I could have actually gone into my calculator at this point, plugged in this equation, and figured out one of my x-intercepts. But we can also use math. Now, I may want to say to myself, if I'm talking about time, can time actually be negative? It cannot be negative. So I'm going to throw out the negative option, and I'm just going to have my time being 5 root 2 over 4. And I'm going to punch that into my calculator so I can get a good idea of what that time actually is. So I'm just punching it into my calculator. And I'm getting approximately 1.77. Let me remind myself what time is in times in seconds. So at approximately 1.77 seconds, this thing's going to hit the ground.